Hello and welcome to Controllers Tech. In the previous video I covered how to use the hardware semaphore for core notification and synchronization. Today we will see how to use the shared memory to transfer the data between the cores. To do so, we will use the OpenAMP framework, along with the remote processor messaging. You can find more info in the document number AN5617. This document specifically covers the inter-process communication. Let's see why we need inter-process communication in the first place. We can use it for event notification, where one core can be used to monitor the event, and it can send the notification to the second core, to wake up and process the event. We can use it to ask for the remote service, where the cores will have to make the request via the IPC channel, if it wants to use a certain resource. We can also use it for the payload processing, where one core can be used to collect the data from the sensor, and another core can process the data. Shared memory is one way to transfer the data easily between the cores. Here you can see in the H7 series MCUs, pretty much all the memories are accessible by both the cores, using one way or another. So in a way we can use any memory region as the shared memory for both the cores. But to keep things simple, I will go with the SRAM4 region, which is available in the D3 domain. The main reason is that since the memory is in the D3 domain, it will remain accessible to both the cores, even if the D1 and D2 domains are in the low power mode. The SRAM4 region is widely used as the shared memory for the message exchange, so we will use the same. There are different ways to notify the cores. They include the hardware semaphores, the XD interrupts, and the send event instruction. We will again use the hardware semaphore in this video. For the communication channel, we have the OpenAMP, which stands for Open Asymmetric Multiprocessing, along with the remote processor messaging, RPmessage. OpenAMP is a framework that provides the software components for the development of the applications for the asymmetric multiprocessing system. On the other hand, RPmessage is a component of the OpenAMP framework, which allows the communication between applications running on different cores. The RPmessage library is based on Virtual I/O, which actually does the communication. So this is our last layer of communication. On top of it we have the RPmessage, and then the topmost layer is OpenAMP, for which we will actually write the code. Just like OpenAMP and RPmessage, we can also use the free RTOS along with the stream buffer for the inter-process communication. We are not going to cover this for now. Then there are some hardware resources also, like hardware semaphores, XD controller and send event instruction, and the DMAs. I have covered the hardware semaphores in the previous video, and the rest of these channels will be covered in the upcoming videos too. Today we will focus on the OpenAMP. In the OpenAMP framework, one core acts as the master, whereas another core acts as the slave. Master and slave both initialize the OpenAMP individually. Then the master creates a new service, and an endpoint, whereas the slave only creates the endpoint. The master sends the data, the slave receives the notification and the callback is called. The slave can then process data, or it can send something back to the master. A detailed instruction is given here on the very next page, but we will follow it while writing the code. We also need to modify the linker file in our project for this to work. So let's start and create a new project in CubeIDE. I am using the STM32 H745 discovery board. Give some name to the project, and click Finish. Let me clear the pinouts first. We will start with the clock setup, and it will be the same as what we did in the previous videos. Now the first thing we need to do is enable the hardware semaphore interrupts for both the cores. Now go to middleware, OpenAMP for the M4 core, and enable it. I am making the M4 as the slave, the rest of the configuration is kept as default. The M7 core has automatically become the master. The master will send the data to the slave, and then the slave will send it to the UART. The board has the virtual COM port connected to the pins PB10 and PB11. These are the TX and RX pins of the UART3. So I am enabling the UART3 for the slave core, that is Cortex M4. Now let's configure the MPU. We will start with enabling the cache for the Cortex M7. Let's also enable the MPU. Let's see the memory configuration first. Here I have the reference manual of the STM32H745. Here in the D3 domain, we have the SRAM 4. This is connected to the BDMA. It is also connected to the D2 domain, via the AHB bus. And also to the D1 domain via another AHB bus. So all the domains can access the SRAM 4, and since it is in a separate domain, it can still work even if the other domains are in low power mode. Let's check the memory organization. Here you can see the start address of the SRAM 4 is at 38 million hex. In the MPU configuration, we will set this region as non-cacheable, so to avoid data coherency. The RAM size is 64 kilobytes. If you don't understand this, check out the MPU configuration videos in the M7 playlist. That's all the setup we need. Click Save to generate the project. Let's build the main files once before we go ahead. Here you can see a separate folder for OpenAMP has been created under both the cores. I am going to start with the M4 core, that is the slave. Here I have defined the RPmessage service name. The variable message received will be used to indicate if the message has been received. Received data will contain the actual data received. The RP endpoint is the RPmessage endpoint structure. Next we have the RPmessage receive callback, which will be called when a new message arrives. Then we have the receive message function, which we will write to receive the data. We will write the callback and the receive message function later. Now inside the main function, after all the initialization has been done, we will write the code for the OpenAMP. Let's understand this as per the instructions given in the document. Right now I am writing for the slave, that is, the M4 core. We need to first initialize the mailbox, which is done here. Then initialize the OpenAMP, and check for the status. If the status is not OK, the error function will be called. Here we are doing the same. The function takes the RPmessage role as the parameter, which in this case is RPmessage remote, the slave. The second parameter is to bind the new service, but since the service is created by the master, here we will just pass the null. The next step is to create the endpoint. Here we will pass the address of the RPmessage endpoint structure that we defined in the beginning. The next is the name, which is also defined. Then the destination, which is set to any available address. Then the callback, which we defined earlier. And finally the unbind callback, which will be null, since the service is not being created by the slave. Now after creating the endpoint, the main loop begins, where we receive the data from the master. Once the main loop is done, we can deinitialize the OpenAMP. Here for the main loop, we will receive the data, then convert it to the string format, and then send it to the UART. Let's define this data array to store the data in the character format. Finally, we will deinitialize the OpenAMP. We still need to write the callback function, and the receive message function. In the callback function, we will first typecast the data to the unsigned int, since this is the format of our variable. After the data has been stored in the variable, set the message received variable to 1, indicating that the data has been received. This received data variable contains the actual data, and we are converting the data stored in it to the character format. Since the data type is unsigned int, we need to use the appropriate format specifier. Alright, now the function to receive the message. While the message received variable is 0, we will keep checking for the data. OpenAMP check for message is used to poll for the incoming message. Once the data is received, the message received callback will be called, the variable will be set to 1, and it will break out of this loop. Here the code is written to receive the data only once, and after receiving, the OpenAMP will be deinitialized. Later in the video we will set it to receive infinitely in a while loop. I haven't defined the status variable, let's define it here. Alright, we have some errors, but they are related to the linker file, so we will fix them in the end. Let's write the code for the M7 core, that is the master. Here we have the similar defines that we used in the M4 core. This time I have defined the RPmessage channel name, and it is the same, OpenAMP test. The message variable is the actual message that we will send via the OpenAMP. This is an integer value, and after receiving it, the M4 core will convert it to the character format before sending it to the UART. We have the similar variables here. The message received is used to indicate if the message has been received. Similarly, the service created will be set to 1, once the service has been created by the master. Received data variable will contain the actual data received by the master. And the RP endpoint is the endpoint structure. We have similar functions for the message received callback, and for receiving the message. Other than them, we also have the callback functions for the service created and service destroyed. These callbacks will be called when a new service is created or destroyed. We will write these functions in a while, let's write the main code first. Let's take a look at the document again, and understand this code. Here we are not using the RTOS, so this part is irrelevant. After initializing the mailbox, we need to also initialize the RPmessage endpoint. Note that we are only initializing the endpoint, it will be created later. Next, initialize the OpenAMP. The role is the master, and this time we need to bind the new service callback here. This is because the service is created by the master, and once the service is successfully created, the respective callback will be called. Inside the callback, we will create the endpoint. So here we will wait for the endpoint to become ready. Now once the endpoint is ready, send the message using OpenAMP send function. Now wait for the service to be destroyed, and then deinitialize the OpenAMP. Let's write the function we defined earlier. Here is the message received callback, and this is similar to what we did for the slave. Although the master is not going to receive any data in today's video, we will use this function in the next one. When the remote endpoint is destroyed, the service destroyed callback will be called, and here we will simply set the variable to 0. Similarly, when the service created callback is called, we will create the endpoint. Here the name and destination is fetched from the new service callback. We have to pass the message received callback, and the service unbind callback. Basically, once the OpenAMP is initialized, the new service callback will be called. Then the endpoint will be created. Finally, we can send the message to the slave. Alright, let's edit the linker file now. We will start with the M7 file first. Copy this part from the document, and paste it in the linker file. We still need to add one more line for the resource table. Now scroll down, and add the section part below the user heap stack. We need to do the same for the Cortex M4 linker file also. That's it, let's build the code for both the cores. The M7 core will send the integer message, the M4 will receive the message, convert it to the character format, and then send it to the UART. Let's flash the code to the board. I am fast forwarding this part, as this is already covered in previous videos. I am using the Hercules for the serial monitor. Here you can see the number 1234 has been printed on the monitor. This value was sent by the M7 core to the M4 core, which then converted it to the character format and sent to the UART. Let's reset the board. The value has been printed again. Whenever I reset the board, the value prints once. So we can say the OpenAMP is working well with the shared memory. Now let's assume the master wants to continuously send the message to the slave. Here I am incrementing the value, and let's set the start value at 1. Here I am putting a while loop, which will run until the message value reaches 15. Let's add a 500 millisecond delay between two consecutive sends. We also need to modify the M4 code, so that it can receive the message continuously. So we will put this much part in the while loop, and comment out the deinitialization for now. Let's build and flash the code into the board. Let me reset the board. You can see the message values are being printed every 500 milliseconds, and they only print up to 14. So we saw how to send some integral value between the cores. In the next video we will use FreeRTOS with OpenAMP, and we will transfer a string rather than just some value. I hope you understood the OpenAMP setup, and how to use it to transfer data between the cores. The link to download the code is in the description below. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.